10?
Yeah.
Or was that one extra credit?
Let me double check
Or
for
is
you.
there another one? And then, okay.
Yeah, that sounded right. Welcome back, everyone. But just to check, let's scroll up to it. Yeah, looks like quiz 10. This one was due Thursday, November 21. And there's also, where did the extra credit go? There it is, that extra credit assignment down below. Well, if you did get that last quiz, the official quiz up here done, don't worry, I will accept them for full credit, even if you turn them in on December 9th, the day of the final exam, I would still accept it for full credit. So just to type back to this comment down here, Monday, December 9th is considered the last official day for all coursework. So that includes the quizzes and the work in my lab as well, or my stats lab. I don't know if we ever decide on the official title for that thing, but aside from that, today we're just doing the same as we did before, reviewing the final exam, but other questions so far? Okay, let's maybe just run down the typical announcements you would expect right before the final exam. So when we come back next Monday, this is the last official week of the entire semester, week 16, but we only meet on Monday. That's it. So there's no Wednesday class and so on. This final exam is going to have one confidence interval problem, and it'll be chosen by random selection, whether it's categorical or quantitative data, and one hypothesis test problem. Same idea, just one or the other. Also, don't forget on the real final exam, you're allowed 2 pages sized 8.5 by 11 inches front and back, handwritten or printed out of notes, anything you'd like on there. So it's a little bit more because, well, the final exam has a way bigger coverage. So just kind of makes sense, I think, say. I'll bring spare calculators, but don't forget to bring yours. It's always better to work with the calculator you're most comfortable with. And aside from that, these are just the review documents down here. Definitely take a look at, say, things like the blank exams and anything that went beyond exam 3, take another look at, and you'll be in really great shape. If you feel like there's a certain chapter that you just need to revisit, maybe it's chapter 14, maybe chapter 5, these documents right here, they're very long, but they're great for targeting a specific chapter one by one. So what we're doing is trying the impossible of going to one document, reviewing the entire course on that, and we left off on this problem right here. Any questions at all, folks, about the announcements before we continue on this one? Okay, so what we did on this problem, just for another quick refresher on the calculator method, we had to import both columns, L1 and L2. So we went stat, enter, and that's where we stored the data. Then the way we produce this equation down below is we hit stat key again, calculate. We need to go way down to option 8, linear regression. That's a point at which we hit enter a bunch of times. And it prints out y equals a plus bx. So we copied that down directly right over here, and then just plugged in the value for a that the calculator cites and the value for b, which was that negative 30,689. So that was the calculator steps getting through this one. Any questions at all, folks, getting to that stage? Okay, so once we get here, I don't know why, but I feel like I want to color code that as well. The y variable just seems off balance. Now we're ready to do some predictions based off the model. And maybe let's just reread the context. I don't know if we even read the context last night when we were looking at this. This says the Kelley Blue Book provides information on wholesale and retail prices of cars. So if you're ever in the market for a new car, that's a site you might visit. Following should have said, following are age and price data for 10 randomly selected Corvettes between 1 and 6 years old. So we can imagine maybe these are Corvettes in Idaho Falls. If we look at, say, the newest model, this is 1 year old and it's worth about $425,000. Some of these models at 6 years old are around $300,000. And that's what we have plotted over here. The age of the Corvette and the price that it would sell for in dollars. And as you expect, these cars depreciate really, really rapidly. Buying a car is the worst investment you could ever make, but it's somewhat controlled. in this sense, if we look at the slope, that's this portion right here, and it says we're losing about $30,689 per year on the value of that car. So now if we want to know what's the predicted sales price for a Corvette that's 2 years old, you might look here, but these are not the predicted sales prices. These are the real sales prices from the data. So we're really wondering, what would the model say if we plugged it inside here? Steps would look like this, y equals, go back to green. So y, the sales price, would be equal to 472,126.21 minus 30,689.32 times the x value. The x value would be this right here, 2 years old for the Corvette. So 2 goes into that position. And now at this stage, we're just jamming it all into the calculator. So 472,126, 21 cents, and then subtract $30,000, $689.32 times 2. So our predicted sale price for this 2-year-old Corvette would be equal to $410,000, $747.57. Compared with what was said right here, that's a pretty good approach. For doing some random math equation, this is actually matching the data pretty strongly. Well, any questions, folks, on the prediction? Okay, with a lot of statistics problems, you might notice it feels like the first part is usually the hard part, where you're doing things like the parameter or the hypothesis test. In this problem, you're importing data and producing the actual linear regression equation. But the follow-up parts are typically a little bit faster, like the part B was on this one. And as far as this goes, this is the problem that is just pure context. We're being asked again, does it make sense to interpret the y-intercept of the least squares regression line? On exam 3, it didn't. We were modeling the amount of oxygen you need for a dive depth. The y-intercept was when x is 0, meaning a dive of 0 feet. It sounds fatal. And so in that case, the y-intercept didn't make sense. But in this problem, we think about the data. A y-intercept will occur exactly when x is 0. That's the best way to tell if it would make sense. So let's write it down right here. At a y-intercept, x would be equal to 0, meaning, what would that mean? Let's go back here. It says age in years, but that's now going to be the age of the Corvette that's up for sale. So this means the Corvette, I probably spelled that wrong. Is that like 2 T's? Something like that. I don't own one. The Corvette is brand new. Thank you. And that's okay. We could certainly ask the question, how much would this model predict for a brand new Corvette? It really would make sense in this situation. So that means we have to give a practical interpretation to it. Let's say here, at the y-intercept, we have y equals, the y-intercept is just this value right here. And you can, if you want, plug x equals 0 to get that y-intercept. It would just delete this whole thing, turning it into a 0. So this portion is the y-intercept. And now what it's saying is we have y equals $472,126.21 is the cost of the new Corvette. So this is one of those cases where y-intercept would make sense. And it's kind of random how that went in the course. About half of them made sense, half of them didn't make sense. But they all pretty much got resolved this way. You always start right here, move backwards to what x is, then that's the best way to tell if it would make sense or not. Well, that's part C done. Any questions on that one? Okay, Last thing is the practical interpretation for the slope of the least squares regression line. Now that we're talking about the slope, we're referring to this portion, just the numerical value. And let me highlight that a little bit better. The slope would also include the negative sign as well. So that's our slope. The very first thing we do with this process is we think about the context. I think a good way to think about that is to look right here on the graph. Let me paste it down below here. So we need the graph and we need the actual slope. Geez, that's a lot of pasting. Now at this stage, I think we can begin. So we can say, to start off, the slope is this part right here, B, whatever it was in the calculator, which is the negative 30,000 and some change. So B equals, numerator is going to be the units for the vertical axis. So we'll write down negative 30,000, 689, 32 cents. And I kind of messed up my unit. Well, I guess I could go like that. Dollar sign and the negatives just kind of look funny next to each other. The denominator is going to be a 1. So no matter what this is, we always put 1 down into the denominator and we write down its unit, 1 year in age. So this right here is not the practical interpretation, unfortunately, but it's just a structure to help us think about what it would really be. So the answer would be right here. We'd say, by looking in the denominator, for each additional year, the Corvette ages the predicted I guess we could say sale price. Let's come over here where the numerator is. Because there's a negative sign, we'll say we'll go down by $30,000, $689.32. So essentially what we were saying all along, that slope is telling us the amount it depreciates per year. We just have to rewrite that statement for this practical interpretation. Well, any questions, folks, on analyzing the slope? Okay, I don't think there's any further parts on this one, so that's pretty much what you could expect for a real final exam question on this one. I don't think I'm going to ask a residual question, mainly because we didn't ask one on exam 2 when it came up. So it feels like it would be a question just out of nowhere. So let's go off then to the next problem, unless there's any further comments on this one. Okay, let me get rid of these temporary screenshots so the notes don't get too busy if you come back to these. And here's our probability question. These make people nervous, and I totally understand. I feel like our book kind of goes through probability really, really quick in that just one chapter, there's loads of concepts. Because of that, I'm not going to make probability a huge actual contribution to your final exam grade. If there's a question on there, it won't be worth too much. And it'll be pretty similar to this one. So watch along with the strategy on this, and it'll be really great shape for the final. And if you make a mistake, it won't be for very much worry or credit on it anyways. So this problem starts by saying, funding for many schools comes from taxes based on the assessed values of local properties. It's kind of an unfair way to put money into schools, but that's the way we do it. It says next, people's homes are assessed higher if they have extra features such as garages and swimming pools. That makes sense. If you have one of those, then the tax assessor is going to punish you for that. Assessment records in a certain school district indicate 78% of homes have garages. And down below here, we have an event G saying the randomly selected home has a garage. This is a good point to start color coding things and writing down some expressions. So from right here, let's write down probability of G having a garage is 7.3 for the 73% chance. Right over here, it says 11% have swimming pools. Let's see, we're using S for the event of swimming pools. So probability of S. In context, if S gets indicated like this, S is not the sample space. It's just referring to some other event. S for swimming pool made sense. So 0.11. And next it says 2% have both swimming pools and garages. So that's a compound event. We can write for that one. Probability, both swimming pools and garages. So it'll be S and G equals 0.02. That's kind of curious data. It seems like in this particular area, you pretty much had one or the other. Only 2% had both the swimming pool and the garage. So, well, that's the whole write-up of the context. Now we have to start calculating some stuff. Looking at some of these things we see here, this would be a typo. Sorry for that formatting. On the real exam, this should be written this way. Probability, G complement, meaning no garage. That symbol there is used for other probability books. It's an intersection symbol, just another way to say and. So let's write it in more appropriately. Again, sorry for that typo there. And S complement. So this is saying neither a swimming pool and a garage at the same time. Okay, so looks like we're ready to take on part A. Let's see, how many parts is this? Just 2 parts. Now, this is a problem you could probably do without a Venn diagram, but if you're a fan of using that approach, we'll try out both. So method 1, no Venn diagram whatsoever. We'll just go like this. If you like the formulas for probability, then the one for this was a probability a randomly selected home has a garage or swimming pool or both. We could take this and rewrite probability. Let me get my colors going again. G or B. This or right here is really pretty special. This or includes the case of having both at the same time, or exclusively the swimming pool, or exclusively the garage. So it's an inclusive or when we indicate it here. So probability of G or B becomes probability of G plus, that looks like a number 8 or something. Let me fix that. Plus probability of B. And this is almost the right answer, except there is an overlap here. We've double counted it if we stopped right here. So we counteract by writing minus probability SNG. Or, hang on, that was an S, and I said S, but I've been writing down B. Sorry about that. These should have been S's. Here and here. And then on this one, I was going to write S and G. Let's go G and S, although it doesn't matter. It makes it look more similar to how you probably normally write it down. G and S. Okay, so once we get to this stage, we're just plugging in values. For probability G, above we have 0.73 coming from way over here, plus probability of S. In blue, we found that that's 0.11. Well, we really just looked it up from the wording of the problem. Probability of G and S right here, we have the 0.02 value. And so we're pretty much done at this stage. This becomes 0.84 minus 0.02 means this should be 0.82, unless I somehow messed up the arithmetic there. That would be the end answer on this one. Well, any questions at all, folks? Doing it just the analytical way, citing the formula and cranking it out? Okay, method 2, or people like to see this in a more visual way, is the Venn diagram. You only have to do this once, I should emphasize. You don't have to do 2 methods, really. But this is what this method would give us. One big box to contain all of the possible outcomes. We start with either one of these events. Let's go with event G. Put in another event S. Now, the overlap here would never really be this big because the intersection is just 0.02. But sometimes we do make it big just so that we can fit the numbers in and actually visualize the intersection. And the very first thing you do put in is that intersection. You know, it might be a good idea to label these first as G and S, especially if you don't have color coding. You want to say what is what on this. Then put the intersection, 0.02, right in the middle. The reason this one goes in the middle is because it's a probability of having both the swimming pool and the garage. And if you're within the green bubble, you have a garage, but notice where the red dot is, it's simultaneously in the blue bubble. So this is having a garage and a swimming pool both at the same time. And it said there's a 2% chance of that happening. So that's what we're trying to convey right here in the Venn diagram. This one is at 0.73, but we can't place that there. We have to place 0.71. Exactly, good call. Because all the numbers in here, well, the 0.71 and the 0.02, the probability, and they add together, that was kind of a weird sound, to the 0.73 if you just subtract first. Then we just do it again. We can't put 0.11 here. It's got to be 0.09. That makes sense so far? Okay, so now when you separate out your probabilities in this kind of way, you really have a little bit more information than what these above really were giving us. There is a 71% chance of having exclusively a garage and no swimming pool, 9% chance of having exclusively a swimming pool but no garage, and 2% chance of having both. I guess these are the lucky ones. And there's even more information here. In the outside, this is the complement of having either one. So the number that goes here is a probability of having no swimming pool and no garage. So what's that probability? Well, probabilities will sum to exactly 1. So we take 1 minus these three numbers. So minus the 0.71, minus the 0.02, minus the 0.09, and this is what we're left with. An 18% chance of having neither one of these amenities. So 0.18 goes right here. And you know, method one, I said method one twice. Let me see if I can fix that. That's a weird typo. Method one is nice because it's really, really fast. But method two is nice because although you take some time to put this down, gives you loads of information that sometimes solves the next question down the line. So here just, and the question, we can say probability, G or S, written this way, this is the probability of having the garage, the swimming pool, or both. It comes out as the 0.71 plus the 0.02 plus the 0.09. So just those three values right here is what are needed. But you might have said there's a better way to add these together. You could just take 1 minus the 0.18, and it gives you the sum right here. But let's go with what we wrote down just to make sure. 0.71 plus the 0.02 plus the 0.09 gives us the 0.82 we were expecting, like we got from method one. And you really didn't have to work this hard like we mentioned. You could have gone directly to the 0.82 by just taking 1 minus this 0.18. It's good to just calculate to make sure. And that's 3 different ways to get this. You only have to do it once. And one more follow-up question. Well, for the one coming up next, I'm not too sure if it makes sense to split it up into method 1 or method 2. This is a tricky one if you did use method 1. You'd have to think of what are these symbols saying. G complement is saying no garage. S complement is saying no swimming pool. It's the opposite of this outcome, having a swimming pool, garage, or both. This is having directly neither. So I guess you could separate this into a method 1, method 2. It would look like this. Method 1 is essentially the complement rule. You can say probability of G complement and, let me fix the letter D there, S complement is going to be 1 minus your prior answer, 0.82, which comes out as the 0.18. So this is saying 18% chance of having no garage, no swimming pool. But we could have just gone over here and met the two and just grabbed that number. So understanding and analyzing the Venn diagram just says, well, it's kind of weird to write this out twice, like I mentioned. It's going to be probability G or S equals 0.18. But let's maybe indicate we did this. We eyeballed the Venn diagram and just pulled it down. I forgot my complements. G complement to S complement. So that's the probability of having neither one of those amenities. Well, there's lots of ways to do these. And I'm not going to ask anything too crazy. We covered a lot of ground in this chapter on probability, but just like on the exam, it was pretty much something like this, similar to the quiz. You can expect something like this again on the final exam if probability comes up. Well, any last questions on getting through those? Okay, let's keep on going down then. Next on the list, more probability, but I think a lot of people consider this to be a funner probability problem because this is just amounts to using the normal distribution. We used that a lot when we went to chapter 13 to do our inferential statistics. So now this is kind of a rehash of that same kind of exercise over here. So we're told, this kind of actually looks familiar. I think we might have solved this problem before. Rochester, New York averages 21.9 inches of snow in December. Because it said averages, we can say either Y bar or mu is 21.9 inches. Well, I think the best approach on this one is there is no sample here. We're trying to estimate the value of mu by that number, 21.9 inches. This is not saying we know mu is 21.9 inches. This is just saying we're going to use the best information we have and say the population proportion of snowfall during the month of December averages this amount. So we're going to claim a parameter value. And I did this something weird again. That's what part A is. I should copy it down here. Mu is 21.9 inches. We're also told the distribution of snowfall amounts is normal. So I'll use the normal distribution with the standard deviation of 6.5 inches. There's no sample here, once again, so it's not a statistic we're analyzing. This is an assumed value for the population standard deviation. We indicate sigma now is 6.5 in inches. So that gets us started. And the purpose of part A is if you used a different value right here, I would know that right away, and I would be able to know you're not going to lose credit again in part B. I would just use your same values to check your numbers. So we're asked, what is the percent chance that Rochester will experience 10 inches of snowfall or less this year? So a really light year for snowfall. They're usually above 20 inches. It asks us to include a graph round to 2 decimal places. I'm not going to take off all credit if you exclude the graph, but that's just a way for me to award partial credit. So here's what it would look like. So this is the normal model. We indicate it by writing n. N is coming from this statement where they said distributed normally. We put in first parameter, 21.9, and the second parameter, 6.5. So just a reminder, first parameter is always mu, second parameter is always sigma, and those are like the last two values that you would be putting into the calculator. So that means this one is centered right at 21.9. Now let's take a look at the question again. It's asking about 10 inches of snowfall or less. So we go to about where 10 inches would be. 2 standard deviations would be about subtracting 13. So it'll probably be somewhere around here, roughly. I'll just say that this is the location for 10 inches of snow. And that's in X inches of snow there. The probability will be just this area towards the left. Now, with this setup, we can now say input one lower should be negative 10 power 99. This is the input two, the upper value, that cuts it off. And we usually set input 3 and 4, but that's always the last two inputs, so we can just jump now into the calculator. Because we're dealing with the area, this problem is a normal CDF process. So is my calculator turned off? Hit second and then bars to pull up distributions. We're in, oh, I went too far, option 2, normal CDF. Those are the 4 inputs we throw in, and I'll go negative 10, power using that button up there, 99. The upper value is going to be 10 inches. Don't forget to change your parameter values. It's honestly easy to forget because if we're doing a hypothesis test, they're always 0 and 1. So that's the new parameter, 21.9, and 6.5. So that becomes our probability to 2 decimal places. Let's see, no, they wanted percentage. So if I round this to 2 decimal places, but I also want a percentage, that's kind of a interesting way to analyze a problem. Let's go times 100 first. Now it's a percentage. And if I'm rounding that as a percentage to 2 decimal places, it's going to be 3.36%. So there is a 3.36% chance of 10 inches or less snow. Well, any questions at all, folks, on getting that percentage? Let me double check my numbers as well. So I'll go second bars, and yeah, normal CDF.
Oh, negative.
That could have done it, yeah. Yeah, without it, it looks like you probably would have gotten the complement or something else. I'm really not too sure. It would have.
Negative, 0.96.
Gotcha. Well, other questions so far? Okay, let's try this out again. Part C is asking, what is the percent chance Rochester will experience between 10 and 20 inches of snowfall this year? So we kind of see how it goes based off the last one. The lower is going to be 10, the upper is going to be 20, and same last two inputs. But just for the sake of connecting the dots on the notes, let's quickly sketch this out anyways. So here's the model. And 21.9. So 21.9 goes here on the center. 6.5. And we're talking about between 10 inches. So that's a cutoff right here. And 20 inches. 20 inches is just right before the mean. I don't like where I put the 20. Let me use the arrow method. There we go. So we want this area this time. But this number right here is going to be input 1. That number will be input 2, the lower and the upper. Same last two inputs here. So at this stage, hit second, bars, down to normal CDF. And that's weird, it kind of resets my values each time. We'll go 10, upper is 20, mu is 21.9, and the sigma is 6.5. So between 10 and 20 inches, this looks like it's a pretty big probability, maybe close to about 40, almost 50%. Let's see if that's close to our expectations. Not quite. This is lower than I would have thought, just below 40%. Well, just above 35% is a more accurate statement. It's asking what is the percent chance. So hit times 100. Now it's a percentage. And to 2 decimal places, this would be 35.15. So we can say there is a 35.15% chance of between 10 and 20 inches of snow. Really, you could have just said 35.15% inches. That's a totally fine answer. But if you did write down a little bit more, that's almost like you're forcing your mind to think about that. If it's even a reasonable response, it's not a terribly bad strategy if you have extra time on an exam.
Put number two as,
This one right here.
yeah, should be the 20 and not.
Oh, yeah, that is weird. I should have been pointing to that one.
I
Thanks
got
for
it.
spotting
I got a
that.
different answer, so I was like, wait, I was just checking all my math, so.
Yeah, I think that one was my bad on this one. I'm going to trust your answer.
It's 20, so the I was at the wrong number, so.
Yeah, that was my bad. What did your answer come out as? I'm going to put this in.
4, 6, oh, 1. I think that's it.
Anyone else have it?
Yeah, I think mine was 4, 6, 6.
Which would mean a 14.67% chance. That sound about right? Let's double check again.
Well, then my answer now is 0.35. Right?
Gotcha. So let me hit second bars down to normal CDF. Oh, and I did have the 10 and 20 inches. That's weird. I was pointing to the wrong thing, but it looks like I did put the right values in. That's
You had the
really
right
confusing.
But then I had the upper as new, and then I had new as well, so that's what.
Oh, I gotcha. So yeah, this one should be a, oh, let me put this back. 35.15% chance. Yeah, sorry for that weird confusion right there. Other questions at the moment? Okay, part D is now asking next. And I think, yeah, we definitely answered this question. I remember this one being kind of an ambiguous question to answer because we have to know, what does a worst case really mean? We'll take this to mean overwhelming amounts of snowfall, so lots of it. We want to know what amount of snowfall in this Rochester, New York place in New York describes the 1% of worst cases for the month of December. So this one's a little bit trickier because if they give you this, it means use inverse norm. So now we're going backwards on this problem. First thing we need to do is put down the actual probability that was given to us. Once again, it's N, let me scroll up, 21.9. Comma 6.5. And let's add some information on the x-axis to help think about this. This is X inches of snow. And we want the 1% worst cases ever, which means we're going to the right tail pretty far, putting down some value. Let's call it maybe something like K, just to have a placeholder there. And this area over here that we've indicated is going to be 0.01 in area. Which means in the calculator now, this will be input number 1 in inverse norm. That's input 2, and that's input 3. Hang on. No, that's not quite right. I mean, that would work for some calculators, but not everybody. The people with the TI-83 and the TI-84, this model TI-84, couldn't actually do that. Let's do it anyways, just to show what it would look like. Hit second. Let me try again. I missed. Hit second and bars. Inverse norm. Now for the people with the fancy calculator, go to right tail 0.01 for area. We can't do that, but let's see what happens if we do that in this calculator. Oh, that's the wrong model. That's the inverse T distribution. Let me try one more time. Second and bars. Inverse norm, like we said, that's option 3. I guess option 4 almost looked too familiar in my mind. Area came out as 0.01. Again, this is the wrong value. You should be really using 0.99. That's such a tricky mistake. I'm showing what it would look like if you did make that mistake, just to show what the correction is. 21.9 for the mean, 6.5 for the standard deviation. If you run this through, you get an answer of 6.77 inches of snow. And we know right away there's a problem then, right? That should have been over 21 inches. So here's the correction. Again, that's my mistake right there. It's true that that's the area, but that's not input one for most calculators used in the class. It's going to be this right here. This is 1 minus 0.01, which comes out as a 0.99 in area. And that's the area that we have to use. So let me put down just a really quick comment. For most calculators, only the area to the left is accepted. And so that's what makes this one input one for area. So we have to use area to the left. And even in the fancy calculators, if you select your tail to the left tail, put in 0.99, you're copying our method exactly and it works in the exact way. You just have options now. You could do either or.
It's right centered and left centered, right? So
Yeah. So back to second vars, inverse norm. Our area is really 0.99. So if you're ever on the right tail, use the complement rule again to get the right value. Hitting all this, now we have rounded to 1 decimal place, 37.0 inches of snow. So we can say here, just to finalize the answer, K equals 37.0 inches or more describes the 1% worst cases. So that's pretty much the rundown on anything that can happen in the calculator through the normal distribution. Again, it's kind of the funner probability problem because this is the one that comes back over and over again. Hypothesis testing being the key example. But any last questions, folks, on that last problem down on the bottom of the notes? Okay, so the notes that we completed all the way down to problem 5 here is the unit on inferential statistics, or excuse me, descriptive statistics. That's what we call the other review problems. Then the other half of the course is way up here, inferential statistics. It was minimized a little bit on the real final exam, so see this right here. I only asked one hypothesis test question and only one confidence interval question, just so the final exam isn't so large. And if we'd like, we could just go down the list. It looks like this one is a hypothesis test. Next one is going to be, see, looks like a confidence interval. So that seems like a good next two problems. Does that sound all right to folks? Just go down the line. Okay, so we've got pretty good variability here on the types of tests. Example 1 says, most like it hot is the title of a press release by a Pew Research Center, is a premier polling agency. The press release states that by an overwhelming margin, Americans want to live in a sunny place. That I would agree with that, especially in the month of December. This statement is based on data from a nationally representative sample of 22,060 adult Americans. So not just Idahoans. As a nation, people like warmer climates, it sounds like. That's enough information for us to start writing down things. Sample size is 2,260 adults. And it says down next, of those surveyed, 1,288 indicated that they would prefer to live in a hot climate rather than a cold climate. You know, that's interesting. I don't know if I'd call that overwhelming. That's half the sample, basically. But let's take another look at this. We have a sample size, and we have information about some members of the sample satisfying a condition, preferring to live in a hot climate than a cold climate. That looks like a success right there. Or we're dealing with successes and failures for categorical data. So let's call this the successes. And this would tell us we have 1,288 successes in our problem. And just to tie this down, this is what we mean by a success. Preferring to live in a warmer climate. Seems to be the target of the study, especially with that title right there now at this point. Now it goes on to say, suppose you want to determine if there's convincing evidence that a majority of all adult Americans prefer a hot climate over a cold climate. Okay, so that's what we want to determine. That's not a question, but it's a statement that could be implied in a question. This is the alternative hypothesis essentially right here.
Then don't you divide the successes by the sample?
Yeah, that would be giving us our, let's see here, our p-hat, so we can calculate the standard error down below there. Absolutely. Other questions at the moment? Okay, we might as well do that one step right here, because let's see here. They say most likely hot is the title of the study, and they say the press release states by an overwhelming margin, Americans want to live in a sunny place. Does our data even support that? Let's take a look. We'd be calculating p-hat, like you had said. Sorry, let me get that going. P-hat is going to be used when we go to deal with the standard error down below, and it's going to be the number of successes, 1,288, divide by the sample size, 2,260, and let's take a look. Came out to an exact 57.
Well, 56.9.
56.9, gotcha. We want to keep it as a decimal number though.
So it's 0.5699.
0.5699, thanks. Awesome, we wanted the 4 decimal places since the final answers also could be rounded to 4 decimal places. And looking at that, I don't know if I would call that an overwhelming margin, at least in the sample, of preferring to live in a warm climate. I would just say, yeah, it's a majority. An overwhelming majority, that sounds like you're talking about at least 60% or more. I think most people would think overwhelming majority, 80%, 90%. That's underwhelming in my opinion. But, you know, this is some study that, or some article they were trying to get sold, I guess. So they had kind of a dramatic title. Maybe that's what was going on. But at this stage, we're ready to start running through the problem. Part A is all about setting up the hypothesis test. So we want a parameter, a null hypothesis. And in this problem, this could happen on the real final exam. We ourselves will choose a level of significance. So let's start off with the type of data. If you said anywhere we have successes, if you thought about calculating p-hat, then the unknown parameter is p, the population proportion of successes. We'll write down p equals, you could say literally the population proportion of successes, and that'd be totally fine. If you want a different option, you could also say this, p equals the true percentage. And we need to mention what the actual population would be. We have adults in the sample, and we're only talking about people in the nation, United States of America. So we'll say true percentage of all adult Americans, really applying United States of America. That, now we mentioned the successes, prefer to live in a hot climate rather than a cold one. Prefer to live in a hot climate. I'll paraphrase it to just that. If you say you prefer to live in a hot climate, I think that implies you do not prefer to live in a cold one. So I think that's a good paraphrase on this one for the parameter. Next, we can say, we will test. Here we put in the null hypothesis, H naught, and that's going to be P equals something. At this point, we might have noticed we don't seem to have yet indicated a value to be tested. Has anyone spotted what it should be? There's one word that signifies it, and this one I think is kind of nasty, kind of the worst ones that we've seen in a while. But this is how people really ask statistical questions, not in the most precise way. We have to find that context word. let's keep on going while we're thinking about that. That's also a decent strategy on the exam. If you're not sure, just move forward and hope your subconscious starts to clean things up and think about it. So we will test this statement, which we'll finalize later, versus the statement, HA, and P comes in again. Let's go back to this statement. We said that this one is a statement of the alternative hypothesis. Suppose you want to determine if there's convincing evidence that a majority of all adult Americans prefer a hot climate over a cold climate. Does that sound like a less than, greater than, or not equals? I agree with you. This would be a greater than, and I think it comes from right here where it says a majority. That's a kind of a nasty word to write into a hypothesis test question. That makes this review question, in my opinion, a little bit tougher than a real exam one. I try to make it less ambiguous. But this is a pretty good experience for statistics in the real world where people are going to throw unprecise words at you. Right where it said a majority, this actually gave us a couple things, but one thing it does give us is right-tailed test comes from that statement right there. So we'll say greater than. Same problem as before, though. And we'll see what goes here. Greater than what? It has to do with that word majority, once again, as a hint. That word majority does two things for us. It chose the test. It also indicated P naught, the value to be tested. Anyone happen to know what it ought to be based off that one word?
No, wouldn't that be the population? So.
It wouldn't be that number. It's got to be a number between 0 and 1. And it comes just from that statement where it says majority. Again, that's an awful word to use on a real file exam. Sorry, say again? It'd be 50%. Yeah, a majority means above 50%.
Oh.
Horrible way to say stuff, right? But people do this to you all the time in real life, and I honestly miss it half the time. Sometimes people make these statements, seems clear in their head, but to everyone else, we're just puzzled. What in the world do they even mean? So statistics is one of those kind of sciences where you just have to deal with that and do the best you can. Makes this a horrible exam question, but it does mean, good call, like you said, it's 0.50 that goes here. And it came from the word majority once again. So if we're being asked, do a majority of Americans prefer to live in a warm climate, we would ask, is P bigger than 0.50? That's a majority. The null hypothesis would be, no, nothing is different. It's exactly 50%. So nothing special there. And last thing we have to do is choose a level of significance. So we're running this hypothesis test at alpha equals, and this is our second time facing this sort of situation. It's a real potential problem on a final exam. We just have to decide what is an appropriate value. Any volunteers for what could go here? I would like that, yeah. 0.01 requires a high level of evidence before we find and we accept the alternative hypothesis. So let's go with a 0.01. Other acceptable values might have been a 0.05, 0.10. If you're feeling fancy, no one's going to stop you from going 0.03. There's nothing wrong with that number either. It's just kind of curious. We like round numbers in statistics, like 0.05, but you can get a little bit fancy there if you wanted to. So now that we got through that, we'll do a little bit of condition checking, and then we can run through the rest of this hypothesis test. As far as the conditions go, like we mentioned in the prior problems, we're only going for 2 overall conditions. Do we have random data is the first question we have. Let's see here. Nationally representative sample of 2,260 adult Americans. That's not telling it's random, but this is a pretty major polling organization. So if you trust them, then it could be as good as random. Down below here, we'll say the sample was indicated to be representative of all adult Americans. That's our population, that are parameter targets, by the Pew Research Center. So if our conditions really don't succeed based off the sample being non-representative, it's on them now. The Pew Research screwed up. But at least we had some information about the sample itself. It wasn't some kind of convenient sample where they select only Idahoans, for example. That would skew the results massively. Beyond that, the second condition we need to take a look at is the sample size even large enough? Usually this passes, especially when you have such a large sample way up here, 2,260 Americans, but we have to actually show what we're going to calculate. So this one is also trickier. It's trickier than the confidence interval. We're not using the successes in the sample. We're using the successes we expect to get if the null hypothesis were true. So we calculate in part 2, expected successes. That's going to be by formula, n times P naught. So that means it's going to be 1288 rather, times 0.5. It's kind of a nice calculation. This will give us, just cut it in half, 644. We only had to be greater than or equal to 10, so we meet that benchmark very nicely. Then we go and turn it around. Expected failures. This is the failures we expect when the null hypothesis is false, which means we would calculate n times 1 minus P naught. But the closer you look at that, you might realize that's n times 1 minus 0.5. That's a 0.5 again. So that's kind of a nice value in your null hypothesis. It means your expected successes is your expected failures right away. So we have, this is equal to 644. Always write the greater than or equal to 10 as a reminder. That's what we had to hit for the benchmark for a large enough sample. So now we can say the sample size is large enough and conditions are met. Although, if you're worried about condition 1, then good on you. You should always be a little bit skeptical when someone tells you, I've got a representative sample, but it wasn't through any kind of randomization. Well, part B is done. Now we're at the fun stage of cranking things out. Part C wants the calculate the value of the standard error coming in next. So where it says standard error, we go down to this formula. And let me think about this a little bit closely. Why would we calculate the value of the standard error? I think this is a typo in the notes, but my apologies for this one. This should have said, let's use a pen that really looks like an error occurred here. This should have said standard deviation in this location. The reason for that is if we're doing a hypothesis test, we assume that the null hypothesis is true, and we actually use the central limit theorem to get the exact standard deviation of the statistic. So it's not a standard error this time. It goes SD P hat. And again, apologies for that typo. That's a pretty serious one, because if you write standard deviation P hat like this, it's a reminder that this is your formula. P naught, 1 minus P naught, divide by sample size n. Very similar to if it were a standard error, you would have just put P hat here and here, but that's only for confidence intervals. So let's calculate this out next. This is going to be square root of, we take P naught times 1 minus P naught. That'll be 0.5 times 1 minus 0.5, or rather just 0.5 times 0.5. Divide it all by the sample size, which was, I forgot. 2260. Yeah, now I'm looking at that. I think I made another mistake on here. Sorry about that, folks. So I'm going to assume I'm just trying to go too fast on this. It was for sample size 2260. And the mistake I made was here. That should have been a 2260 as well. 2260, and that means when we cut that in half, that should have been 1130. Does that make sense with that error right there? Looks like what I grabbed was 1288. I was looking at the successes. My eyeballs should have been here. We should be looking at the sample size when we go to plug in for n. So that should have been a 2260, and that means 1130 here, and also 1130 right here. We meet the conditions either way, but it's weird to put in the wrong numbers in those two spots. So now back to this one, we just need to compute this into the calculator. Let's power this thing on, hit second, and power 2 key, kitty corner left and up from the 7 key, go 0.5 times 1 minus 0.5 is just another 0.5. Divide by 2260, and we have our standard error. To 4 decimal places, it's 0.0105. That look all right so far? Okay, on to the next exciting step. Once you get your standard deviation, you want to calculate this test statistic right away. So that's why it's the next part. So the test statistic is going to measure how many standard deviations was p hat away from the statement in the null hypothesis, 0.50. So we go and calculate like this to start. The test statistic is going to be z. This is just a reminder when you write down z, we're using the normal distribution for the p-values. The format goes p hat minus p naught divide by standard deviation of p hat. So now in this problem, we're going to get our p hat came out as a 0.5699. We're going to subtract off from that just the 0.5. And now down below is 0.0105. So back to the calculator. It's just another z-score like we did yesterday. 0.5699 minus 0.5 divide by the 0.0105. And this is our resulting z-score, or rather test statistic. It's beyond 6 standard deviations. So looks like just about anything you put here for the significance level, we were going to reject the null in favor of the alternative either way. So that's quite significant. 6.65, 71. Well, any questions, folks, to that stage? Sorry, just struggling with the calculator. Okay, so next step, we need to get our p-value out. Here we need to remind ourselves now at this stage, what was the hypothesis in the first place? So we go up to the very top, pull out the parameter and your hypotheses. Let's just park it down below here when we're about ready for the practical interpretation. And this is the computation finally for the p-value. If you like, you could do a really quick sketch just to show how it all comes together. So here's our normal curve. This one is n, 0, 1. So in the center, we've got 0. And next is the test statistic. That's 6.6571. it's astronomically far away from zero, so it's not even really easy to plot that thing. Let me try just to do the best we can. Plot here, which doesn't look accurate, but it organizes the information at least. Area being shaded to the right, which is incredibly small, is going to be our p-value. And last thing to say now is we're going to use normal CDF. This right here is input 1. Input 2 is going to be 10 power 99, since our area is moving to the right forever. That's input 3, and that's input 4, 0 and 1. So we're using the standard normal distribution. So back to second bars, go down to normal CDF. Lower is the test statistic on this one, Z, and I should have wrote that number in. That looks kind of weird. 6.6571. So that's our lower value. Upper value, 10 to the power 99. We would put infinity if we could, but the calculator can't support infinities. And last is 0 and 1. So putting that all in, this is your p-value. It's stated in scientific notation, so that's a good indication. Again, you are probably going to reject the null hypothesis whenever that happens. Let's write down on paper the p-value equals 1.40 times 10 to the power negative 11. So if you really want to write this down without scientific notation, you would go 0 point. I need to put in how many zeros? I think about 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 140. And let me double check that. I always feel nervous about scientific notation. I should move this right 11 places and land on this spot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So yep, that's our p-value. You don't have to expand your scientific notation, but this is more if it ever came up in your calculator and you're doing a MyStatsLab problem, that's really what you're looking at. Whatever it is, scientific notation or in standard form, we can definitely now say that this is less than 0.01, which is equal to alpha, which means we reject H naught. We found significant evidence that P is bigger than 0.50. There is a majority, in other words. The level of evidence is overwhelming, but looking at the statistic again, it's still 56%. So we have overwhelming evidence that it's barely above 50% is what this is all trying to convey now. Well, last stage is the practical interpretation. Any questions whatsoever, folks, with the p-value? Okay. So I do agree with the authors when they said there is overwhelming evidence that's supported by your p-value being astronomically small in a certain sense. Let's start by saying we have overwhelming amounts of statistical evidence to support the claim that, yeah, we can come down here and you really have two options. You could say your answer is we have overwhelming evidence to support the claim that true percentage of all adult Americans that prefer to live in a hot climate is above 50%. Or you could just simply say a majority of Americans prefer to live in a hot climate, and that's fine as well. You're using their same language back at them in their conclusion. They probably would appreciate it. I'll just do the standard thing that we're kind of used to doing. I'm going to read out the hypotheses that we wrote just verbatim. It's more specific. It's easier to understand. I think it makes a better interpretation. We'll say that the true percentage of all adult Americans that prefer, I'll just say, paraphrasing even more, prefer warmer climates Now we can come over here and say is above. And now 50%. So that finalizes that one there. And whoa, geez, that was all the time. That kind of ended right at the second. Sorry about that. I wasn't looking at the clock too carefully on that one, but hey, we made it to the last problem. Well, this last problem that we could get through. There's still 3 more inference problems down below in these notes. So if you decide to use this document for further study, I will be solving these and uploading them after I get caught up on grading on Friday. So I should have results posted probably, I'd say at the latest Saturday afternoon, if you want to come back and check out the rest of these. Otherwise, have a great weekend, folks. Try to get lots of rest. Don't go crazy and try to do any all-nighters. That's pretty rough on finals. Other good advice is if you're a coffee drinker, you want to definitely drink your normal amount of coffee. If you're not a coffee drinker, don't take a bunch of coffee before an exam. You'll be in the wrong mental space. Try to keep your mental space in the same place where you study. And that's the best time or the best place to be in when you actually take your exam. But have a great weekend, folks. If you're working and you have questions, please don't hesitate to email me. I'll get right back to you.